Hello everyone, I am Abhradeep Das, a material scientist at Paanduv Applications, and today in this presentation I will be discussing about the computational potentials of the software that we have developed. This particular session is for the collaboration between Addisol and Paanduv Applications. I will be talking about one of our flagship products, that is AM PravaH, that is designed for an end-to-end additive manufacturing solution for the entire workflow, where we will be simulating the processes across different length scales. Starting with about the introduction about us. This particular software is a brainchild of Mr. Advait Gupta, who has been the lead developer of AM PravaH, and at Paanduv Applications we are based in India, and at Paanduv Applications we will be dealing with the computational scientific solutions provided for multiple problems that are dependent on CFD and different aspects. So in the context of AM PravaH, I would like to highlight about the different length scales that are actually operable in case of an entire workflow. So starting with the micron to Armstrong's length scale, what we can see here that the length scale where we are actually operating into relies between somewhere between micron scale to beyond millimeter scale. So these are the area where we will be operating. Our simulation software solutions are delivered for across these different length scales, that is starting from the micron scale to the beyond millimeter scale. So with AM PravaH, we tend to work on three fundamental additive manufacturing processes, which is laser powder bed fusion and wire based direct energy deposition techniques, which includes wire laser DED and wire arc DED processes. Starting with some of the validations of the particular software, what we have observed and what we have uh, reached so far is that we have validated the synchrotron X-ray images and tend to understand the subtle physics of this particular problem, and with our simulation tools, without performing even the experimental tools, and we can have an idea about how this particular process governed by complex phenomena is actually operating in. You can clearly see from these results that how accurately the particular phenomena is captured, considering the different manifolds of this particular process, which includes the defect formations and tending to different melt pool profiles. That's what we are doing for the melt pool dynamic simulations. Some other subtle features that we would be solving in our multi-phase multi-physics software solutions, it includes the laser changing the different laser beam profiles so that we can have different thermal histories and we can generate different sorts of material properties, and that's what we tend to do with the laser powder interactions, the capture the complex phenomena like the Marangoni convections, also the transient heat treatment and transient temperature profiles that are evolved during the entire process. With that in aid, I would like to demonstrate certain defects that we have captured quite successfully, and that involves the deep physics that is within the formation of these sorts of defects in these innovative processes. We are not restricted to a single layer process. We have extended ourselves to multi-layer processes as well, capturing the all the subtleties in the of the processes itself. For the microstructure, it is one of our interesting modules. What we have observed that the process parameters govern the microstructure formation, which eventually leads to the formation of different properties. So this is what you can see here, and how exquisitely we have captured those areas which are left over in the experimental. That's how we reduce the reliance of the experimental exhaustion for the researchers across the globe and for the engineers who have been working in this particular field. We use the in parallel the four-phase multi-phase problems along with the different Monte Carlo based models to model this microstructure solution. Here is one of the another validation that you can see that we have accurately captured the deviations of the grain sizes as well, wherein you can see that we have validated our results against the experimental EBSD analysis, and we can also see that we are extended to Wire-DED based processes, which includes the WLAM and WAM, which wherein in this front we can see here there are experimental images and we have the simulation against it. Here we have not only captured the wire laser interaction, we have captured the wire different modes of metal deposition from the wire into the substrate. We can also see that in the WAM, as we solve the fundamental equations of the fluid as well as the electromagnetics that we have included for this particular module, we can see here that there are the subtle defects, that is the over and under depositions, are also captured quite well. With our validation studies, we assure you that the solutions, that the simulation that we are providing in the terms of simulations are quite accurate and are in close agreement with the experimental results. So, in a nutshell, I present AM PravaH as an end-to-end simulation software that includes starting from the powder preparation, including the processes like powder atomization, to a part scale simulation wherein we are completely building the entire part and simulating it. We have observed that we with using this sort of software, physics assisted software, you can cut down the cost by around 67% in the range of process optimization and material innovation. It has been an integral part in the part qualification for specific custom products such as aerospace and biomedical as well. Also, we reduce, with the aid of such softwares, we reduce the reliance over the experimental trials and the necessary characterizations for the materials, and that's how it saves the time and it saves the exhaustive resources, and that's how we tend ourselves as a solution for that as well. We have emerged as a virtual twin for the entire AM workflow, not just for the powder based processes. We are here for the Wire-DED based processes as well. That's what uh, we can see here, that the additive manufacturing process chain is entirely covered with our software. So this is a GUI interface of AM PravaH, which is pretty simple, and also we take up values for the independent thermophysical properties, and it's a built it comes with a independent material database that we are providing in the software as a drop down, and it has customizable shielding gas, that is you can vary different sorts of different sorts of inert gases, and that's how you control what should be the optimum parameters that requires for the shielding gas to be operable. We have also customizable powder distribution depending upon your needs. You can change that. We have different scan patterns to be imported here in the software. We have the ability to vary different process parameters with the software, and also we have the capability of changing the different simulation performance parameters that governs the entire work set. We also augment the software with the capability of AI that requires building of data sets. That is be an excellent tool for the material innovation aspect. We have a Q module that reduces the human intervention into the process and reduces the human reliance over the entire workflow that you may have designed. So that's all from my end, and I would like to present the company as an entire solution for the entire additive manufacturing workflow system. And thank you for attending this presentation, You can find out our links for the tutorials for knowing about us in the description below.